Paris, France. The year is 1873. François Barthélemy Alfred Royer de la Bastille stands in his private laboratory, staring at a pile of broken glass. He's a gentleman of fortune, not a glassmaker by trade. He doesn't need to be here, sweating over furnaces and oil baths, but he can't stop. For years, he's been obsessed with a simple question. Why does glass have to be so fragile? He picks up another sheet of glass, heats it in his furnace until it glows orange, almost molten. Then, carefully, he lowers it into a bath of heated oil and grease. The glass hisses and steams. He waits, pulls it out, examines it. It looks the same as regular glass. Clear, smooth, unremarkable. But then he takes a hammer and strikes it. Hard. The glass doesn't shatter. It holds. De la Bastille allows himself a smile. After years of experiments, countless failures, and dozens of formula adjustments, he's done it. He's created glass that doesn't break like glass should. Glass that's strong, resistant, practically unbreakable. Within a year, he'll patent this process in England. It will be called Bastille glass, and it will change everything. But here's what makes this moment so fascinating. De la Bastille didn't invent tempered glass. Not really. He invented a way to make it useful, to manufacture it at scale, to turn a scientific curiosity into an industrial product. Because the secret of unbreakable glass, that had been hiding in plain sight for over 200 years, in the form of curious little teardrops that could withstand a hammer blow but would explode into powder if you touched them wrong. This is the story of tempered glass. It's a story that spans centuries, from mysterious glass drops that baffled kings and scientists, to a French gentleman's obsession, to the material that now protects you in your car, your phone, and your home. It's about how sometimes the most important innovations come from asking why something works the way it does, and then figuring out how to make it work better. And it starts not with de la Bastille, but with a German prince and a gift that nobody could explain. London, England. The year is 1660. Prince Rupert of the Rhine, a German-English army officer and amateur scientist, has just returned from the continent with something unusual in his pocket. They're small glass objects shaped like tadpoles or teardrops, a bulbous head tapering to a long, thin tail. They look like nothing special, really. Failed glasswork, perhaps. The kind of thing that happens when a drop of molten glass accidentally falls into a bucket of water. But these little glass drops have a secret. Prince Rupert presents them to King Charles II, and the king is immediately intrigued. He calls for a hammer. A courtier hands him one, probably thinking the king has lost his mind. Charles places one of the glass drops on a table, head side up, and brings the hammer down hard. Nothing happens. He hits it again. Still nothing. The glass doesn't crack, doesn't chip, doesn't even scratch. It's as if the hammer is striking steel, not glass. This, in an age when glass was notoriously fragile, when wealthy people kept glass vessels under lock and key because they were so easily broken, is nothing short of miraculous. But then someone, perhaps the king himself, perhaps Prince Rupert, touches the thin tail of the drop. Just a light touch, barely any pressure. The entire drop explodes, not shatters, explodes. In an instant, with a sharp popping sound, the glass disintegrates into fine powder. There's no warning, no cracks spreading. One moment it's there, seemingly indestructible. The next, it's dust. The king is fascinated. He immediately passes the remaining drops to the newly founded Royal Society, England's premier scientific institution, for study. If these glass objects can be both unbreakable and explosively fragile, there must be some principle at work, some natural law that could be understood and harnessed. The Royal Society's members, including the brilliant Robert Hooke, set to work. They grind the drops to determine the thickness of the strong outer layer. They encase drops in metal to retain the pieces when they shatter. They conduct experiment after experiment, trying to understand what makes these drops so strange. What they discover is that the drops have enormous internal stresses. When molten glass hits cold water, the surface solidifies almost instantly, but the interior is still hot, still liquid. As it cools and contracts, it's trapped by the already solid outer shell. This creates a state of tension. The surface is under extreme compression, squeezed inward, while the interior is under extreme tension, pulled outward. This is what makes the head so strong. Any crack that tries to form on the compressed surface is immediately sealed shut by the compression forces. The glass at the surface is effectively hardened, toughened, far stronger than ordinary glass. But it's also what makes the tail so deadly. At the thin tail, the tensile interior comes dangerously close to the surface. Break through that compressed outer layer, even slightly, and you release all that internal tension at once. The crack propagates at incredible speed, over 3,000 miles per hour, researchers would later discover, bifurcating repeatedly, turning the entire drop into powder in milliseconds. Prince Rupert's drops, as they came to be known, became a sensation in the 17th century society. They were party tricks, scientific demonstrations, philosophical puzzles. Samuel Butler referenced them in poetry. Samuel Pepys mentioned them in his diary. For educated people of the time, knowing about Prince Rupert's drops was a mark of sophistication, but they were just curiosities. Fascinating, yes, but useless. You couldn't make anything practical from a tadpole-shaped piece of glass that might explode if you looked at it wrong. The drops did prove something important, though. Glass doesn't have to be fragile. Under the right conditions, glass can be remarkably strong. The question was how to harness that strength without the explosive fragility. That question would wait 200 years for an answer. To understand why de la Bastide's achievement mattered, we need to understand what glass was like before him. Glass is ancient, really ancient. The earliest known glass objects date back to around 2500 BCE in Mesopotamia, where people made glass beads and decorative items. For millennia, glass was precious and rare, made in small quantities by skilled craftsmen who guarded their techniques jealously. The big breakthrough came with the Romans. Around 50 BCE, glassblowers in the Syro-Palestinian region invented glassblowing, the technique of inflating molten glass by blowing air through a hollow tube. This revolutionized glassmaking. Suddenly, you could make thin-walled vessels quickly and cheaply. Glass went from a luxury material to something ordinary Romans could afford. As the geographer Strabo noted, by the 1st century CE, you could buy a glass drinking cup for a copper coin. Roman glassmakers became incredibly skilled. They made everything from simple bottles to elaborate cameo glass, from window panes to intricate mosaics. They understood how to color glass by adding different minerals, copper for blue, manganese for purple, cobalt for deep blue. They developed mold-blowing techniques that let them mass-produce decorated vessels. But Roman glass had one persistent problem. It was fragile. A dropped glass vessel shattered into dangerous shards. A thermal shock, hot water poured into a cold glass, could crack it instantly. This limited how glass could be used. It was fine for containers that sat still, for decorative objects, for windows in wealthy homes. But for anything that needed to withstand stress or impact, you used metal or ceramic instead. When the Roman Empire fell in the West, much of this glass-making knowledge was lost or scattered. Medieval Europe had glass, certainly. Stained glass windows became one of the glories of Gothic cathedrals. But glass objects remained fragile, precious, and limited in application. Even as glass-making revived during the Renaissance, even as Venetian glassmakers created spectacularly beautiful objects and jealously guarded their techniques, the fundamental fragility of glass remained. Drop it, stress it, heat it unevenly, and it breaks. That's just what glass does. This fragility wasn't just inconvenient, it was dangerous. As industrialization accelerated in the 19th century, glass was being used in more applications: factory skylights, greenhouse panes, scientific equipment, and increasingly in transportation. In the 1860s and 70s, as de la Bastille was conducting his experiments, trains were becoming faster and more common. Carriages were evolving toward what would become automobiles. And one problem kept emerging: glass breaking and injuring people. A stone kicked up by a wheel could shatter a carriage window, sending sharp fragments into passengers' faces. A railway accident could turn glass windows into deadly projectiles. Even in stationary applications, glass was a hazard. A factory skylight cracking from thermal stress could rain razor-sharp shards onto workers below. Glass needed to be tougher. Ideally, it needed to be both stronger and safer, able to withstand more stress before breaking, and when it did break, to break in a way that didn't create large, dangerous shards. De la Bastille understood this. He wasn't trying to make glass for art's sake. He was trying to make glass that could serve new industrial and transportation needs, glass that could be trusted, and he had a clue to work from: Prince Rupert's drops. If those could be unbreakable, if that compressive stress made glass strong, maybe there was a way to create that same effect in useful shapes, in sheets, in panes, in practical forms. François Barthélemy Alfred Royer de la Bastille was not a typical inventor. He was born in the year 1830 into a comfortable Parisian family. He had private means. He didn't need to work for a living. He could have spent his time in leisure, in society, in any of 100 gentlemanly pursuits. Instead, he spent it in a workshop, trying to make glass unbreakable. We know frustratingly little about de la Bastille's personal life. There are no detailed biographies, no collections of letters, no journals revealing his thoughts. What we know comes from his patents, from contemporary accounts of his work, and from the impact his invention had. But we can imagine him, this French gentleman scientist, in his private laboratory. He would have understood the basic principle from Prince Rupert's drops. Rapid cooling creates compression on the surface, and that compression makes glass strong. The question was how to achieve that in flat sheets of glass, not just tadpole-shaped drops. His first attempts probably followed the drops too closely, heating glass and plunging it into cold water. But this caused the glass to crack from the thermal shock, or to warp, or to develop internal stresses so severe that the glass would spontaneously shatter days or weeks later. Water cooled too quickly, too unevenly. It was too violent. De la Bastille tried different approaches. What if the cooling medium was less severe? He experimented with cooling glass in air, but this didn't create enough compression. The glass was barely tougher than ordinary glass. Then he had an insight. possibly borrowed from metallurgy. Blacksmiths had known for centuries that you could harden steel by heating it and then quenching it in oil. The oil cooled the steel fast enough to harden it, but not so fast that it cracked. What if the same principle worked for glass? Late one evening, Delabasti prepared a bath of heated oil. He heated a sheet of glass in his furnace until it was almost molten, glowing orange in the dim workshop. Then carefully, he lowered it into the oil bath. The glass hissed and steamed, but it didn't crack. He left it in the bath, watching the temperature gauges, waiting for it to cool. When he finally pulled it out and let it reach room temperature, it looked normal, just a pane of glass. But when he tested it, dropping it, striking it, subjecting it to thermal shock, it held. It was stronger, not unbreakable, but noticeably, measurably tougher than untreated glass. He was on to something. Over the following months and years, Delabasti refined his process. He found that the bath didn't need to be pure oil. In fact, a mixture worked better. Oil, wax, tallow, resin, other fatty ingredients. Each adjustment changed how the glass cooled, how much compression built up on the surface, how strong the final product was. He also discovered that temperature was critical. The glass needed to be heated to just the right point, soft enough that the molecules could move, but not so hot that it lost its shape. And the oil bath needed to be at a specific temperature too, warm enough that the glass didn't cool too rapidly and crack, but cool enough that it cooled rapidly enough to create the necessary compression. It was painstaking work. Each experiment took hours, heating the glass, preparing the bath, going through the tempering process, then testing the results. Many pieces failed, cracking during the process or shattering spontaneously afterward. But gradually, Delabasti got better results, stronger glass, more consistent glass, glass that didn't just survive his tests, but excelled. In the year 1874, he filed for a patent in England, patent number 2783. The patent described his process in detail, heating glass to near its melting point, then quenching it in a heated bath of oil or grease, producing glass that was dramatically stronger and more resistant to thermal shock than ordinary glass. He called it tempered glass, though some people began calling it Basti glass in his honor. Delabasti wasn't thinking about car windshields or smartphone screens. Those technologies didn't exist yet. His patent emphasized uses like tableware, decorative objects, containers. Glass that could withstand hot water without cracking. Glass that wouldn't chip or break from normal handling. Glass that was, as he wrote, more durable and more perfect than ordinary glass. But he had unlocked something bigger than he probably realized. He had taken a 200-year-old scientific curiosity, Prince Rupert's drops, and turned it into a manufacturing process. He had made unbreakable glass practical. The immediate impact of Delabasti's invention was modest. Yes, some manufacturers adopted his process. Yes, people made tempered glass products. But glass tempering remained a specialized, relatively expensive process. The equipment was complicated. The technique required skill. And for many applications, ordinary glass was still good enough. It would take new demands, new technologies, new dangers to make tempered glass essential rather than optional. Within 3 years, in 1877, German inventor Friedrich Siemens developed an alternative tempering process. Instead of oil baths, Siemens used cold molds, pressing hot glass into cool forms, creating compression through the rapid cooling of the surface. His glass was even stronger than Delabasti's, though the process was more limited in the shapes it could produce. Other inventors followed. In 1935, Austrian chemist Rudolf Seiden obtained the first comprehensive patent for a complete tempering process, one that would become the basis for modern tempered glass manufacturing. But the real transformation came with the automobile. In the late 19th and early 20th centuries, as cars evolved from experimental contraptions to practical vehicles, glass became a critical safety issue. Early cars had no windshields or only rudimentary ones, but as cars got faster, windshields became necessary. You needed protection from wind, rain, insects, and debris. The problem was that car windshields shattered in accidents, and when they shattered, they created vicious, blade-like shards that caused horrific injuries. Drivers and passengers were being lacerated, sometimes killed, by their own windshields. In 1903, French chemist Edouard Benedictus accidentally discovered laminated glass, glass with a layer of plastic sandwiched between two panes. When laminated glass broke, the plastic held the pieces together, preventing the dangerous spray of fragments. This became the solution for windshields, but for side and rear windows, laminated glass was expensive. This is where tempered glass found its calling. By the 1920s and 30s, automobile manufacturers were beginning to use tempered glass for side and rear windows. When tempered glass breaks, it doesn't form large, sharp shards. Instead, it shatters into small, relatively harmless granules, thousands of tiny pieces, rather than a few lethal blades. This is because when the surface compression is finally breached, all that internal tension releases at once, fragmenting the entire pane. In 1937, Henry Ford mandated the use of tempered glass for side and rear windows in all Ford vehicles. Other manufacturers followed. By the 1950s, tempered glass was standard in automobiles across America and Europe. The automobile industry drove massive improvements in tempered glass manufacturing. Producers needed to make it faster, cheaper, more consistent. They needed to be able to temper curved glass for windshields and windows. They needed quality control that ensured every piece would perform as expected. This industrial demand pushed innovations. By mid-century, manufacturers were using forced air systems instead of oil baths, heating the glass in furnaces and then blasting the surfaces with carefully controlled jets of cold air. This was faster, cleaner, and more precise than Delabasti's oil bath method. They also developed chemical tempering, where glass is immersed in molten potassium nitrate. The smaller sodium ions on the glass surface are replaced with larger potassium ions, creating compression without heating and cooling. This process can temper complex shapes that wouldn't survive thermal tempering. But the principle, creating surface compression to strengthen the glass, remained exactly what Delabasti had pioneered and what Prince Rupert's drops had demonstrated 2 centuries before him. Today, tempered glass is everywhere, and I mean everywhere. The shower door in your bathroom? Tempered glass. If it breaks, it shatters into granules instead of spears, preventing serious injury. The side windows in your car? Tempered glass, strong enough to withstand normal stress, but designed to fragment into small pieces in an accident. The glass door at your local bank or store? Tempered glass, resistant to impact and safer if it breaks. Your smartphone screen? That uses chemically strengthened glass. Essentially, a descendant of Delabasti's insight, using chemistry instead of heating and cooling to create surface compression. Gorilla Glass, the most common smartphone glass, can withstand remarkable abuse because of this principle. Even your kitchen, Tempered glass is used for oven doors, for glass cookware, for cutting boards, anywhere that glass might experience thermal stress or impact. In architecture, tempered glass enabled entirely new possibilities. Glass skyscrapers became feasible because tempered glass could be made large and strong enough to serve as actual structural elements, not just decorative features. Glass balustrades, glass floors, glass roofs, all possible because of tempering. The numbers are staggering. Millions of tons of tempered glass are produced every year. Almost every car on the road contains it. Almost every modern building uses it. It's become so common that we barely notice it, even as it protects us constantly. And when tempered glass does break, it breaks safely. Those thousands of small granules might be startling, but they're far less likely to cause serious injury than the large, sharp fragments of ordinary glass. This has saved countless lives and prevented innumerable injuries over the past century. Think about what would be different without tempered glass. Cars would be death traps, side window glass shattering into deadly shards in even minor accidents. Shower enclosures would be genuinely dangerous. A slip and fall could be fatal if you went through the glass. Smartphones would crack and splinter at the slightest drop. Modern architecture, with its soaring glass facades, wouldn't exist. Delabasti's invention, building on 2 centuries of scientific curiosity about Prince Rupert's drops, fundamentally changed how we interact with glass. It took a material known for its fragility and made it strong. It took a hazard and made it safe. And he did it by asking a simple question. If glass can be strong under certain conditions, why can't we create those conditions deliberately? Let's return to Paris, to Delabasti's workshop, but this time years after his patent. The year is now 1880. Delabasti, now 50 years old, still maintains his workshop. His process has been adopted by manufacturers across Europe. He's been granted additional patents, refined his techniques, seen his invention spread to new applications. One evening, he receives a package from a glass manufacturer in England. Inside is a pane of glass, perfectly clear, smooth, and unremarkable to look at. But the accompanying letter explains that this pane has been tempered using his process. It will be installed in a railway carriage, protecting passengers who will never know his name, will never think about the years of experiments that made their journey safer. Delabasti holds the pane up to the light. It looks exactly like ordinary glass. That's the beauty of it, really. You can't see the stress, can't see the compression that makes it strong. It's invisible engineering, protection hidden in plain sight. He thinks about how far this has come, from curiosities that exploded when touched to a manufacturing process that can produce strong glass at scale. From a scientific puzzle to an industrial standard, he knows there's more to be done. The process could be faster, more efficient. Different compositions might make even stronger glass. New applications will surely emerge as other technologies develop. But for now, in this moment, he allows himself satisfaction. He solved the problem he set out to solve. Glass doesn't have to be fragile anymore. The story of tempered glass is really a story about persistence and connection across time. Prince Rupert brings curious glass drops to London in 1660. They baffle the Royal Society's greatest minds. They're studied, marveled at, but remain impractical curiosities. 2 centuries later, Delabasti looks at those same principles and sees not a curiosity, but a challenge. How do we make this useful? How do we harness this strength? He spends years experimenting, trying different cooling mediums, adjusting temperatures, testing formulas. Many inventors would have given up. Delabasti had private means. He could have abandoned this frustrating project at any time. But he persisted. In 1874, he succeeds. He creates a practical process for tempering glass. But even then, the impact isn't immediate. The technology needs time to find its applications, needs other technologies, like automobiles, to create demand for it. By the mid-20th century, tempered glass is everywhere, saving lives, enabling new architecture, making modern life possible in ways large and small. And researchers are still studying Prince Rupert's drops. In 1994, scientists used high-speed photography to capture cracks propagating through drops at over 3,000 miles per hour. In 2016, they measured the exact stress distribution using advanced optical techniques, finding compression forces of up to 700 megapascals, equivalent to 100,000 pounds per square inch. These studies aren't just satisfying old curiosity. They inform how we make ever better tempered glass, how we understand stress and fracture in materials, how we design safety glass for new applications. This is how innovation works in reality, not as sudden breakthroughs, but as accumulating insights across generations. Prince Rupert's drops demonstrated a principle. The Royal Society studied but couldn't explain it fully. Delabasti saw how to make it practical. Industrial demands drove refinement and scale. Modern science reveals the detailed mechanisms. Each generation builds on the last. Each makes the next step possible. The next time you get into a car, take a moment to look at the side window. It looks like ordinary glass, clear, smooth, unremarkable, but it's not ordinary. It's stronger than you'd think, tougher than it appears. Hit it hard enough and it will break, but when it does, it will shatter into thousands of small pieces instead of a few deadly shards. That difference has saved countless lives. Or look at your phone screen. Drop it, carefully, ideally, and notice how resilient it is. That's chemical tempering at work, the same principle Delabasti pioneered, just applied in a different way. Tempered glass is one of those inventions that becomes invisible because it works so well. We don't think about it. We don't notice it. It just protects us, quietly, constantly, in dozens of ways throughout our day. But it required someone to look at a scientific curiosity, glass drops that were both unbreakable and explosive, and ask, how do we make this useful? How do we make this safe? How do we make this practical? François Barthélemy Alfred Royer de la Bastille asked those questions, and for over a century, his answer has been keeping us safe. That's the invention of tempered glass, an ancient principle, a patient investigation, a practical solution. Glass that's strong because someone refused to accept that fragile was the only option. From Prince Rupert's mysterious drops to your car window. From a 17th century party trick to 21st century smartphones. All connected by a simple idea. Glass under stress can be incredibly strong. You just have to create the right kind of stress, in the right way, for the right purpose. And that's what Delabasti did. He turned stress into strength, fragility into safety, curiosity into protection. That's tempered glass. That's the unbreakable discovery.